Last time we talked about acids and bases, their characteristics, and their pH readings. This time we're going to take a little more in-depth look at acids and bases and figure out what makes a solution an acid versus a base. Our first question is, how or why do acids and bases conduct electricity? And so remember last time in the notes we said that both acids and bases, one characteristic of them is that they conduct electricity. And this is why. Acids and bases conduct electricity because there are ions in them. Remember, ions are charged atoms. So what acids and bases do when they're mixed with water is they what's called dissociate. Okay, they go through dissociation, which basically means they just break apart into the ions that make them up, or the charged atoms that make them up. So, for example, acids can dissociate like we see here. HCl, when in water, can break apart into H ion and a chlorine ion. Bases as well also dissociate. NaOH, which is a popular base that we've used in many labs, can break apart or dissociate into sodium ion and what we call a hydroxide ion. Okay, so these charged atoms from the acids and bases are going to give them the ability to conduct electricity. Now let's take a look and see which particular ions are important for acids and bases. And when we do that, we're going to come to our second question, which is, what is the Arrhenius definition of acids and bases? So this is the first guy who thought of solutions being acidic versus basic, and he had a very simplistic definition of acids versus bases. He said, acids are any substance that adds a hydrogen ion to the solution. So if a substance falls apart and releases that H plus ion, then it is considered an acid. Bases, on the other hand, is any substance that adds hydroxide ions, or that OH minus ion, to the solution. So when it dissociates, it's going to have that OH minus ion in it. So this definition is pretty simple. Acids release the H's, bases release OH's. So it works for the obvious substances like these, right? HCl breaking apart into H plus and Cl minus. H2SO4 breaking apart into, again, H plus and then the SO4. We also see bases, NaOH, breaking apart into Na plus OH, so there's the base part, and NH4OH breaks apart into NH4 and OH, again, that base part. Okay, so these you can see within the chemical formulas if they're going to be an acid or a base. Here's the OHs in the bases, and here's the H's out front in the acids. So it works for those obvious substances, but what about the ones here on the bottom, right? These were some of the ones that we tested in our pH lab, and but they're not obvious, right? Washing soda, Na2CO3, doesn't have any H's or OH's in it. However, according to our data, it indicated as a base. Okay, so how's that possible? Lemon juice is another example. Its formula is C6H8O7. Again, no inherent, really, obvious H-OH kind of combination within its formula. So, but we know from the indicator that it is an acid. So how do we figure that stuff out? So let's take a look at our next question, which is going to help us expand the definition of acids and bases. All right, so here's our third question. What is the Bronsted Lowry definition of acids and bases? Now remember, it was the two guys here, Mr. Bronsted on the left and Mr. Lowry on the right, who came up with this expanded definition of acids and bases together. So that's why it's called the Bronsted Lowry. Okay, so their definition helps us include those not so obvious substances that we saw at the end of the last slide. So here, in this definition, acid is a substance from which a proton, an H plus, remember, hydrogen only has one electron, so when you lose it, all you have left is a proton. So an H plus, hydrogen ion, is also called a proton. Okay, so it's a substance from which a proton can be taken. Okay, so it's called a proton donor. So an acid is a proton donor because it gives away one of its hydrogens. So if we take a look at the lemon juice that we saw in the last slide, okay, if we mix lemon juice and dissociate it with water, we can see that we get, instead of C6H8O7, in the end we end up with C6H7O7. So that means the lemon juice here gave away one of its hydrogens to water, right? Gave it to water, so we ended up with H3O with a plus sign instead of H2O. Okay, so because hydrogen gave away or donated its proton to water, it's what we call an acid. Okay, now a base, on the other hand, is a substance that can take a proton or a hydrogen ion from another substance. So it's going to add the hydrogen ion to itself. It's not going to give it away, it's actually going to take it. And so bases are what we call proton acceptors. So if we take a look at the washing soda from the previous slide, Na2CO3, if we mix it with water, he's actually going to take a hydrogen, right? If we take a look at the end product here, we have an extra hydrogen within this Na2HCO3. So he takes a hydrogen with him and becomes NaHCO3 with a little positive. So he becomes a positive charge. And if we take a hydrogen away from water, right, we end up with OH in the end. So we can see here that in this case, a base is going to take away a hydrogen from water, so we can still leave that OH behind. Okay, so that's what we call a base. So it expands it from saying just everything with an OH in the formula is a base. Well, also the ones that take a hydrogen away from water is also considered a base because we're left with that OH behind. All right, our last question is kind of one that'll make you think. So is water an acid or a base? Okay, so a lot of times when we mix substances, we are going to, dilute them in water. And so water actually can act as either an acid or a base. So it can be both. It just depends on what it's hooked up with. Now, when we look at the equations here, we're always going to have on the reactant side an acid and a base together. Okay, so let's take a look and identify what's what. So here in NH3, this is ammonia, and we add it to water, we're going to end up with an ammonium ion and a hydroxide ion. Okay, so let's take a look and see how water acts as an acid. Well, we see here that in this equation, we start with NH3, but we end up with NH4. So that means NH3 is a base because he's a proton acceptor. He took a proton or an H from water, right? So he makes him a proton acceptor or a base. Now when we take a look at water, we start out with H2O, and one of the H's gets stripped from him. So now all we'll end up with is OH minus. Okay, so in this case, NH3 is our base, and H2O is the acid, because we always have to have one or the other. You're never going to have two bases together or two acids together. Okay, so you're always going to want to distinguish one between the other. Remember, the NH3 turns to NH4 in the end, so that means he is the proton acceptor, which makes him the base. And H2O loses or gives away a proton, so that makes him a proton donor, which is the acid. Okay, now on the other side, we can see this different kind of wording here. It's also an acid and a base, but it has this conjugate in front of it. Okay, this is if we are looking at the reverse direction. Okay, so the conjugate is going to look at the reverse direction of this reversible equation. So if we look at it backwards, Okay, NH4 is going to turn into NH3, so that means he gives away his proton, so he's a proton donor. So that makes him, if it's a proton donor, that makes him an acid, but since it's on the right side of our equation, we're going to call it a conjugate acid. And on the other hand, OH on the right-hand side, when we look backwards in the reaction, is going to gain another proton to become H2O again, and so that means he's a proton acceptor, so he's going to be considered a base. But again, instead of being a full base, he's what we call a conjugate base. Okay, so bases, like on the left-hand side, a base is going to be similar to its conjugate acid on the other side, and a acid is going to be coming from the the conjugate base on the other side as well. So those kind of go hand in hand. Okay, so let's take a look real quick and see how water can act as a base this time. So remember, a base is a proton acceptor. So let's take a look. In this equation here, again, it's a reversible reaction. We have HNO3 being diluted in water, and so we're going to get some ions as it dissociates. So HNO3, if we take a look at before, it's HNO3, and after we have just NO3. So it gave away its H. So again, if it gives away an H, that means it's a proton donor, or what we call an acid. Okay. Now, water, on the other hand, okay, starts out with as H2O and ends up as H3O. So he took, or he got the hydrogen from the acid. So if you're a proton acceptor, you're what's called a base. So in this case, water acts like a base because he goes from H2O to H3O. He accepted a proton. Okay, and then if we take a look again at the reverse reaction, we're going to see the difference between conjugate acids and conjugate bases. So if we look backwards, we can see that the H3O is going to give away its hydrogen to become H2O, so that means he's a hydrogen donor or a conjugate acid. And NO3, if we look in the reverse direction, is going to end up as HNO3. So that means he is a proton acceptor. He took the proton from the hydronium atom. So, or the hydronium ion, I should say. So because he took the hydrogen, he is a hydrogen acceptor and therefore considered a base. And in this case, a conjugate base, since he is on the right-hand side. He's the ion base. Okay? All right, so that's it for these notes, and we'll see you tomorrow for some kind of labeling and categorizing of acids and bases using these two different ways to look at acids and bases, whether they are proton donors or acceptors, or whether they are releasing H's or OH's within the solution.